Hey everyone, welcome back. So now we're going to move on and keep going with our chemistry unit. Last couple of note sessions, we've talked about different forms of bonding. When we first came back from spring break, we delved into single, double, and triple bonds. Remember, single bond is the sharing of one pair of electrons, or two single electrons being shared between atoms. Then we talked about double bonds, which is the sharing of two pairs of electrons, or a total of four electrons being shared. Then we talked about triple bonds, which is three pairs of electrons, a total of six. I'm going to do a review in just a second with pen and paper. Then we went on and talked about covalent and ionic. Covalent is the sharing of electrons, which occurs between two nonmetals most often. When you get into general chem in your junior year or so, it's going to have a little bit of a difference. But for right now, for IPC, that is what we're talking about. Then we talked about ionic bond, which usually occurs between a nonmetal and a metal, and is the transference or the complete transfer of electrons from one atom to another. Specifically, the metal is going to give its electron to a non-metal. Doing this creates oppositely charged ions. You will have a cation, which is a positive, which will come from your metal, and then you'll have an anion, which is a negative, which comes from your nonmetal, who took the electron. Remember, positive charge, you give it up. You've given money away. You're not negative to anybody. You're not in negative standing or anything like that. The anion has taken more than what it started, so it becomes negative. That's just like you go to the bank, you go and borrow $20,000. They give you $20,000. That is more than what you started with. Now you are in negative standing with your bank because you owe them money. Okay? Then we went on to talking about counting atoms. We figured out that if we are given a molecule or a compound, we can count of how many certain atoms, say if we have how many carbons we have, how many hydrogens we have in that molecule or compound. And then we were able to see how many total atoms we have in that molecule or compound. We are going to now go further into that discussion and be able to see how to balance. So now we're incorporating everything that we've just learned about bonding and counting atoms all into one. Okay? That's what we're starting off today. I'm going to do a quick review on covalent and ionic and single, double, and triple bond on paper. So let's get started. All right, so let me get this little handy dandy notebook in. So if you were to look, if we take sodium, we bond sodium to chlorine. Chlorine starts with 7 electrons. He needs one more. Sodium has one valence electron. So they go to each other, they can bond, it makes a single bond. Or one pair of electrons is bonding these two atoms together, which is a total of 2 electrons between them. Now remember, if you break this bond, chlorine will take this electron and give sodium the boot. That will turn sodium into a cation, or a positive charge, and this will turn chlorine into an anion, or a negative charge. He becomes angrier than what he was before because now he is in the negative. Let's move on and talk about double bonds real quick. So if we take carbon and 2 oxygens, this was in your note summary for bonding, specifically for bonding. If you bond carbon to 1 oxygen, one of those 2 oxygens, you are going to form a double bond. They're going to share 2 pairs of electrons, or a total of 4 electrons. Carbon also bonds to that second, so this would be 1 carbon and 2 oxygens. He will bond to the carbon on my left with the double bond, which is sharing of 2 pairs of electrons, or a total of 4. This is a double, and remember, oxygen is a nonmetal, carbon is a nonmetal. We will call this a covalent bond. Okay, let's go down to our triple bond real quick. So you have nitrogen. Nitrogen, each one of them have 1, 2, 3 single electrons on each nitrogen. Those single electrons can bond together and make a triple pair. So it's a triple bond sharing 3 pairs of electrons, or a total of 6. And each nitrogen comes into relationship with its own lone pair, which they keep. This is a triple bond. This was, when we talked about single, double, and triple, this was before covalent and ionic. So when I asked you what 3 types of bonding did we discuss during our bonding notes, this was before we brought up ionic and covalent. We talked single, double, triple. Real quick, tying this into our covalent and ionic. Nitrogen, both of them are nonmetals. So this would be considered a covalent bond because they are sharing those electrons. So that is where we are, and then we count it atoms. So if we count it here, we have 1, 2 oxygens and 1 carbon for a total of 3 atoms in carbon dioxide. All right, now let's move on to this session. We are going to go ahead and talk about starting on balancing chemical equations. So last semester when we talked about physics, there was a law that I brought up. We're going to revisit that just a little bit. So before we do that, let's take a look at our topic, which is balancing chemical equations. This is just adding on to counting atoms. Our essential question is, how is a balanced chemical equation written, and how does it illustrate the law of conservation of matter? For this, we can also say mass. So matter and mass. It's the same concept. So how does this illustrate the law of conservation? So before we move on, let's define what the law of conservation actually means. So last semester, we talked about it kind of in physics, where you cannot create nor destroy matter. Here in chemistry, it's the same thing. You cannot create nor destroy matter or mass. So whatever you start with, you're going to have the same thing in the end. You're going to have the same mass. It might be in a different form, but it's going to add up to the same mass. So just like if you were to bake a cake, you have all of those raw ingredients in a bowl. You weigh it out, it's about 500 grams. Throw it in the oven, you bake it, it becomes this nice, fluffy, yummy, glorious smelling cake. You pull it out, you weigh the cake. The cake itself is a solid. It's going to weigh less than what that liquid weighed. And that's because some of that air and water, specifically water, has evaporated out of that cake to make it solid. Okay? So the water out of that cake evaporated a little bit. So the water is out in the atmosphere. If we were to be able to capture that water back, we'll be able to add that to the cake that we just baked, and it would be the total same. So for the law of conservation of matter, we can even say mass. It can mass of a chemical reaction, during a chemical reaction cannot be created nor destroyed. So specifically, I'm going to add a few more words. So during a chemical reaction, your products or what you end up with, so products of a chemical reaction must equal the mass of the reactants or what you start with. So for example, I'm going to write a chemical equation real quick right below this to show you. Let me find another pen, ballpoint pen. Here we are. So for example, if I take methane and say a methane tank blows up, you add, that is adding oxygen to that tank of methane when you blow it up. So it's CH4, this is a 2 right here, O2, and when that blows up, it creates carbon dioxide and water. Okay, so right now we can see we have one carbon, one carbon, one carbon, and one carbon. If I go to my hydrogens, I'm like, oh wait, hold up. I have 4 hydrogens here, but only 2 here. That's not the same thing on either side. So I'm going to see what I can do for that in a second. If I go to my oxygen, I have 2 here, 2 here. That's 4, because 2 times 2 is 4. But if I go over here, I have 2, 3. That I didn't end up with what I started. So there is a way in chemistry we can change these numbers, just like in math, to be able to see that we ended up with the same thing that we started with. This is how we can do it. We ended up with 2 molecules of water. So if we go here, 1 carbon, 1 carbon, we go to our hydrogens. Oh, 2 times 2, we have 4. We have our 4 hydrogens. If we go to our oxygen, we have 2 times 2 is 4. 4 oxygens on our reactant side. 2. And then we have 2 times 1 is 2. We add those, and we have 4 oxygens on our products. That is how we can see that what we started with, we have to end up with the same mass. We ended up with 2 different compounds than what we completely started. We started out with 1 molecule, 2 molecules of oxygen gas, and 1 molecule of methane. We ended up with 1 molecule of the compound CO2, and we ended up with 2 molecules of the compound of water. That we have the same mass for each one of those atoms. And that is the law of conservation of mass. Now we're going to go on and slowly introduce different pieces of how we're able to balance this and keep the law of conservation. So let's go on. We're going to introduce Snell coefficient. I told y'all this last note session. If you have a big number in front of parentheses or in front of a compound or molecule, all you're going to do is take that coefficient and distribute it within that parentheses. So here, how to count atoms with the coefficient, you have 2 times 2, we have 4 hydrogens. We can pretend there is a 1 right on the back end of that oxygen. So 2 times 1 is 2 oxygens. Okay. Now we're going to move on and talk about what do we do if we see a subscript on the outside of a parentheses. This is the same idea as if we have it on like this hydrogen up here. But here's the thing. If it's outside of this entire molecule, just like this coefficient gets distributed inside, this gets distributed inside. Now this is going to be tweaked a little bit when we add the coefficient and the subscript. So here for our subscript, outside of the parentheses, we have 2 oxygen atoms and we have 2 hydrogen atoms for a total of 4 atoms. Okay. Now I'm going to give you a minute, take a second, and work on that for a minute. Sorry, my husband decided to call me during this whole note session. I just had to text him and say, hey, I'm kind of busy, leave me alone. All right, so now we're going to go on to the next section. How to balance compounds with coefficient and subscripts. All right, so if we were to take, say, this hydroxide, just this one that we're messing with right here, and say if we were to add, actually, I'm going to change it just a little bit. Sorry, I'm not going to mess with this. I'm going to do aluminum sulfate. Aluminum sulfate. And I'm going to do 2 molecules of it. So that is, I'm going to write this one out. I have 2 Al subscript 2 SO4 and a subscript 3. See, this is a perfect example of where I have a coefficient in front of this entire compound with a subscript right on the outside of a parentheses. Okay, so this is, I need you to pay attention really closely with this. When you have a coefficient in front of this entire compound, this is one compound. This coefficient is going to be distributed throughout this entire compound. So for every atom, you multiply it with this coefficient. Oh, I just realized I'm using Mardi Gras colors. All right, so if we were to look at this, we know we have 4 aluminums, we have at least 2 sulfurs, and we have at least 8 oxygens. Now this is where we can get a little tripped up. Okay, I'm going to introduce this subscript on the very far right hand side at the bottom of the parentheses. That subscript outside of the parentheses only gets distributed to those atoms inside that parentheses. Okay, so this 3 on the outside of this parentheses does not apply to that aluminum. It only applies to what is inside of that parentheses. So we can draw a little arrow going here, as well as, that's almost too close to that color. Let me get that to a pink. and this 3 will get multiplied into this sulfur. So if I were to write it all over here, I can see I have 2 aluminums, but I know there's a 2 in front, so it's 2 times 2, which equals 4. So I have a total of 4 aluminums, 4 aluminum atoms. I can say I have 2 sulfurs here multiplied by this 3. So I have sulfur 2 times 1, because there's originally 1 right here, which equals 2. And then multiply that by 3, which equals 6 sulfur atoms. I'm going to circle my ending totals for each atom. Now let's look at my oxygens. My oxygens, I had originally 4. So oxygen at a original 4, so 2 times 4 is 8. But then I have a 3, meaning I have 3 compounds of sulfate. So 3 times 8 equals 24 oxygen atoms. This means I have a total of 34 atoms total for aluminum sulfate. I had 4 aluminums, because 2 times 2 is 4. I have 6 sulfur, because remember, 2 times 1, which is 2, times 3 is 6. Then I have my oxygens, which originally are 4 times 2 times 3, which is 24. And I add all of this up to get 34 atoms in aluminum sulfate. All right, now we're going to go on and look at something else. Let's go down and we'll see 2 iron hydroxide molecules. So this will have a coefficient, but will not have a subscript on the outside. So all I do here is 2. I multiply 1 iron times 2, 1 oxygen times 2, and 1 hydrogen times 2. So I have 2 irons, 2 oxygens, and 2 hydrogens. I'm going to give you a moment for that one. Okay. We'll move on to barium sulfate. So barium sulfate formula is 2BaSO4. I'm going to draw a little line because I'm going to do one extra example on the other side. So I'm going to make sure I have room. So I can take this 2, there's a pretend 1 here, pretend 1 here, and there's 4 oxygens. So multiply 2 times 1 for barium. Oh, sorry, there's supposed to be an A right there. So barium 2, and then I go to sulfur. 2 times 1 is 2 for sulfur. And then I can, then a 2 times 4 for my oxygens. I have 8 oxygens. This will give me a total of 10, 12 atoms in barium sulfate. So there's 12 atoms in 2 molecules of barium sulfate. All right, like I said, we're going to do one more. I'm going to do one more, and then we're going to move on to looking at chemical equations. So on my right-hand side, I'm going to do one more example. So I'm going to do calcium nitrate. The formula are 2 molecules to be specific of it. So the formula for this is 2 calcium, open parentheses, NO3, close parentheses. So that 3 is a subscript on that oxygen. The subscript 2 right outside of those parentheses. So again, I take this coefficient and I'm going to pretend there's a 1 here and a 1 here on the nitrogen. I'm going to multiply for my calcium. 2 times 1 equals 2. For my nitrogen, again, it's 2 times 1. But we cannot forget that subscript on the outside. We're going to get to that in just a moment. And then my oxygen is 2 times 3 is 6. But again, can't forget that subscript. So let's go back and do those subscripts real quick. So if I take 2 and I said that goes only to the molecule inside that parentheses. This 2 only gets distributed inside the parentheses. So that 2 goes to nitrogen. So 2 times 2, because I originally had 2 times 1 equals 2. I have a total of 4 atoms of nitrogen in this entire compound. Now, if I were to take, for oxygen, I have 6 from 2 times 3, but I need to multiply that by my little subscript on the outside of parentheses. So 2 times 2, 6 times 2, I have 12. So I have a total of 2, 4, 8, plus 12 is 20 atoms. 20 total atoms in 2 molecules of calcium nitrate. Oh, there we go. Sorry about that. I didn't realize that was off screen. All right, give you a moment to write that down. So as you're doing that, I just want you to remind you, we've looked at chemical equations this entire semester. I showed you one right at the beginning of this note session with methane and oxygen. Now we're going to go in and look at more chemical equations. Here's one of how we form water. All right, so this is the chemical equation for the production of a water molecule. So I'm going to take this arrow and draw a little squiggly line down. Everything on the left-hand side of this chemical equation, you need to have this drilled into your brain. This is going to be on your test. I will ask you on your test, what is the left side of a chemical equation called? And you will tell me, these are my reactants, what I start with. I will ask you, what is the right side of a chemical equation called? And you will tell me products. This is what you end with. Many of you had issues with this last 9 weeks when we tried to cover chemical reactions. So the left-hand side are your reactants. The right-hand side are your products. You need to drill this into your brain because this will be asked to you on a test. All right, let's move on. Okay, now we're going to go in and talk about balancing chemical equations. This is exactly where the law of conservation of mass will be exhibited. You'll be able to see this. So balancing chemical equations, you will determine I'm trying to make sure I word this right. If the equation is balanced, making sure your reactants and products are equal. So you will determine if an equation is balanced, making sure your reactants and products are equal amounts. So we're about to go down and see this. I'm going to do everything, my first step, all in one color, and then I'm going to do my second step in another color. So you'll see this. So if I look at this, remember my reactants are all on my left-hand side. So if I look at this, I have 3 iron. So Fe is iron. I have 2 hydrogens. And I have 1 oxygen on my reactant side right now. On my product side, I have 3 irons. I have 8 hydrogens. And I have 4 oxygens. I notice that both of my ions are equal. Check. My hydrogens are not equal. And my oxygens do not equal. So my first round through this is the equation balanced. No, it is not. So what I can do is I can go through here. Here's a little thing for it. I always start with my hydrogens. Hydrogens rule everything. So if I look at my product side, I was like, okay, I have 4 on my right-hand side, which is my products. I only have 2 on my left-hand side, which is my reactants. So what were I to do if I drew a 4 in front of my hydrogens here? If I did a 4, I'm going to do it really small to see what I can do. I'll have 4 times 2 is 8. I will have 8 hydrogens. Then I see I have 4 oxygens on this side. I have 4 oxygens here. Bingo! I know that's correct because then I go to my iron. I didn't have to touch that. So if I multiplied everything in my water molecule by 4, so if I go 4 times 2, which is 8, and I have 8 hydrogens on this side, 8 hydrogens on my reactant and my product side now. I already had 3 irons on each side. That's a go. Now I can do 4 times 1 on my oxygen. Sorry, 4 times 1, which is 4. And I had 4 oxygens on my left side and now 4 oxygens on my right side. Is my equation now balanced? Yes. So when you do math like this, most likely you will want to do it in pencil, because trying to do this in pen, if you mess up, it may take you several tries to be able to get this correct. So doing it in pencil will probably be your best bet. Let's go down to the next chemical equation. This is your breathing equation. So when you breathe, you take in oxygen, you exhale carbon dioxide. Through eating, you ingest a sugar, which is the C6H12O6. That is just a sugar molecule for glucose. And when you ingest oxygen, you produce carbon dioxide and water. Now let's go through and see this one. So carbon, on my reactant side, I'm going to do all steps, first steps in red, and then I'm going to do any type of math in black. So I have 6 carbons on my reactant side. I have 12 hydrogens on my reactant side. And I have 6 plus 2, because I have 2 right here and 6 here, is a total of 8 on my reactant side. Let's go over to my product side now. I have 1 carbon. I have 2 hydrogens and 3 oxygens. That's not balanced, is it? Nope, that's not balanced. So now we're going to go on and see what we can do to make this balanced. My thing is, like I said, I always start with my hydrogens. My hydrogens rule my equation. So if I look at my hydrogens, I have 2 over here, 12 over here. What can I multiply by this 2 to equal 12? What if I do 6? So if I do 2 times 6, that's 12. So I have 12 hydrogens over here, 12 hydrogens over here. Okay. I have 6 oxygens here, 2 here, that's 8. How many oxygens do I have here? 8, okay. That sounds pretty good. But wait a minute, I'm still not good with my carbons. Oh, snaps. I'm just not done yet. So this molecule is complete. What can we multiply our carbon by to get the 6 over here? Can I just multiply that by 6? But if you look, I have now 6 carbons, but I have 6 times 2 is 12, plus 6, that's 18. I have 8 over here on my reactant side. So we have to do a little bit more math. If we look at this oxygen right here, we don't want to mess with this one because this one's way too big to mess with. That will throw everything off. We can look at our single molecule of oxygen gas. If we multiply this one by 6, okay, so we're good on our hydrogen, carbons and hydrogens here. If we go and multiply 6 times 2, that's 12. And we have our original 6. 6 plus 12 equals 18 oxygens. 12. Okay, so that's 18 and 18, that's 36 total atoms on my reactant side. But I have 18 oxygen, 12 hydrogen, and 6 carbons. Let's go back to my product side. If I go 6, 1 times 6, that's 6. Bingo for my carbons. My hydrogens, 2 times 6 is 12. Bingo on my hydrogens. Now if I have 6 hydrogen, oxygens, 6 oxygens here, and 6 times 2 here, that's 12 plus 6 equals 18 oxygens. And bingo, bingo, there goes all of my atoms. I have 36 on each side. All of my atoms are equal. So my equation now is balanced. Yes. So let's go down and let you look at that for a second. All right. Let's go down real quick and do a couple more practice. So what happens if we look at this and we go, what the world? I have aluminum here. I have one aluminum, but I have 3 chlorine here on my product side. I only have 1 on my reactant side. Okay. I have 2 hydrogens on my product side and 1 hydrogen on my reactant side. So 1, 1, 1 all across on my reactant. I have 1 aluminum on my product side. I have 2 hydrogens on my product side. 3 chlorines on my product side. What can I do about this? Okay. So remember, let's start with our hydrogens. We have 2 here on my product side. And I have 3 chlorines. They started off together over here. So how could we possibly do this? What if I were to take this side? Let's see. How could we do this? Could you think of a way and test this one out real quick? Pause the video and check it out. Okay, so I hope you paused and looked at it and try to figure it out for yourself. But if you notice what I did on my reactant side, I always start with my hydrogens. So if I multiply 3 times 2 on my hydrogen, I got 6. Because I know this 3 on the chlorine and 2 on the hydrogen, that was going to be hard. So I have to figure out what can I multiply by those to get the same product for my reactant side. I know I can multiply 3 times 2 to get 6. I know I can multiply 2 times 3 to get 6. So that leaves me with 6 hydrogen. I have to have 6 molecules of hydrochloric acid on my reactant side. And I have to multiply, if I have 6 chlorines on this side, I have to multiply my product side, my aluminum chloride, by 2 to get 6 chlorine. That means I have to multiply aluminum by 2. So I have to have a 2 for my aluminum on my reactant side. All right, so let's go down a little bit more and do a couple more practice. I want you to pause the video and try these 2 equations out before we move on. So we have C3H8 plus O2, which would give us carbon dioxide and water. This is a combustion reaction. Then you have photosynthesis, where plants intake carbon dioxide, they release water, or they intake carbon dioxide and water because they absorb the water and they take in carbon dioxide from the air, and they produce a sugar, which is glucose, and oxygen gas, which both of those two we consume to do our respiration. So work on those 2 problems, pause the video, and work on those. It's supposed to be 3 and then 2. So I'm hoping you pause the video to try this out. Oops, I missed a step right here. So 6 times 2 is 12 plus, so this is not totally finished. So that's 12 plus 6, because 6 times 1 is 18. 18 oxygens on that side. All right, so let's run through these real quick. So practice 1, if we started with 3 carbons, 8 hydrogens, and 2 oxygens. That's what we started with before we put our coefficients. On our product side, we started with 1 carbon, 2 hydrogens, and 3 oxygens before we put our coefficients. Once we put our coefficients, because we looked at our hydrogens, go, okay, I have 8 over here. I have 2 over here. Okay, I can multiply this side by 4 to get me my 8 hydrogens. But then that gets me to 4 oxygens here and only 2 here. Or 4, 5, 6. Okay, but then I'm like, okay, my carbons aren't balanced. I started with 3 on this side, on my reactant side, and started with 1 on my product side. Okay, I can do 3 times 1. That gets me my 3. But then that gets me 6 oxygens for my carbon dioxide on my product side, and 4 on my water side for my oxygen. So that's 4 plus 6 is 10. I needed to get 10 oxygens. And that's why I multiplied 5 times 2 to get 10. So I noticed if I go down and I looked at my reactant side and I looked at my product side, I now have 3 carbons on each side. I have 8 hydrogens on each side, because 1 times 8 is 8. 4 times 2 is 8. Go to my carbons. My reactant side, 5 times 2 is 10 on my oxygens. And on my product side, I go with 3 times 2 is 6. And 4 times 1 is 4. 3 times 2 equals 6. Plus my 4 equals 10. Those are all balanced. Let's go to photosynthesis. I made a little boo-boo here. It's supposed to be 3 oxygen, because 1, 2, and 3 right there. And then 2 hydrogens, which are on my water molecule right there. So 1 carbon, 3 oxygens, and 2 hydrogens is what I started with. Everything I end up with is going to be in red. On my product side, I started with 6 carbons, 12 hydrogens, and 8 oxygens. These little X's show me that does not equal each side. My reactants and my products did not equal when I first started. So then I had to go and do a little bit of magical math. So I'm like, okay, on my product side, I see I have 12 hydrogens. On my reactants, it's 2. What can I multiply my 2 to get 12? 6 times 2 gets me 12. So I multiplied my reactants, hydrogens, by 6. That gets me 12. But then I realized I have 6 times 1 for my oxygens, which is 6. And I still had my 2 over here, which gave me 8. I have 6, 7, 8. That would be great, but then my carbons are freaking forgotten about. So I've got to figure out, okay, my carbons are still not pleased. So I need to figure that out. So I had to multiply 6 on my reactant side to get my 6 carbons. So 6 times 1 here is 6, but then I'm like, oh, snaps. My oxygens are not balanced now. Son of a bleeps. Then I have to go back to my product side and go, okay, I have 6, and I have 2 over here, that's 8, but I have 6. Now I have 12 right there, that's 18. God bless America. So now I go, okay, 6 plus 2 is 8. But if I do 6 times 2, that gives me 12, plus my 6 here, that gives me 18. And I had 18 in my reaction. Oh, yes, I got my 18. And it is checked off. I am balanced and I am done. So that is how we balance chemical equations. Yes, it is going to sometimes take you trial and error. It's going to take a moment, but all this is multiplication, distribution, and addition. Everything that you've learned in algebra. And I've told you at the beginning of the year, this is why I love my science class so much, because I can incorporate every single one of your classes, English, math, even social studies, I can incorporate all into one class. So that is balancing chemical equations. So we talked about if it is not balanced, we will have to figure out a way to make it balanced. The law of conservation says we cannot leave it unbalanced. What we start with, we have to end with the same number of atoms on both sides of our chemical equation. So, where's my other paper? So, like we said, the law of conservation from our last two examples, we saw by being able to write our chemical equation, we exhibited the law of conservation. What we start with for every single atom, so 3 carbons, we had to end with 3 carbons. 8 hydrogens, we had to end with 8 hydrogens. 10 oxygens, we ended with 10 oxygens. They were just in different forms. This oxygen was attached to hydrogens to produce water. On my reactant side, it was oxygen gas that we actually breathe to be able to survive. So that is balancing chemical equations. If you have questions, or if you need anything, let me come back over here. So if you have any questions or any concerns, please email me or jump into the Zoom tutorials or Zoom class periods to be able to have those questions answered. So until next time, see you later.